Let me show you another example. This time it's from biology. Let's say we would like to investigate the growth of population, let's say flies, depending on different media. So let's say we have two different media, and this is time. So this is time, and this is the population in number of flies, for example. Okay. Then what we do, we put some certain number of flies, that's our initial population, to the media and count how many flies we have after each time point. For example, we ended up with something like this. Okay. So you can see that at the beginning the population is growing. Okay. Now what we can do, we can also take another media and put the same amount of flies in this media and see what's going on with the population. Let's say we got the data something like this. Okay. So visually we can see that actually the growth of the population in the second media, in the red media, is larger than the growth of the population, or faster than the growth of the population in the blue media. But how to compare this numerically? Again, what can we do? We can fit these two sets of points with some curves, with some known function, like this. And in this case, if we talk about population, it can be quite natural to use exponential function, at least at the first phase. So we know that this is the exponential function, bx, okay, where, if you don't remember, a is a constant 2.7 something. Okay. So y in this case is the number of the flies, and x in this case, it will be a time. It will be time. Okay. So now we can identify these two parameters a and b for each media. So we have a equal to a1 e b1x, and then we have y equal to a2 e b2x. So we have two parameters. We have a2, b2, we have a1 and b1. Okay. So if you remember from the school, a1 is, again, it's what will be y equal to if x is equal to 0. So it's this initial number of flies we have in each media. So apparently we will have the same. And b1 and b2, it's coefficient that tells how fast y will grow. So actually this is exactly what we want. So if we estimate b1 and b2, we'll find out that b2 is larger than b1. And we can use coefficient b as a measure of the population growth, so how fast the population grows. Okay, and that's the same idea. Look, we have some experimental data, then we feed this data with a known function, theoretical function. We find parameters of this function, and then we use these parameters to describe the data and to compare the data. So that's again a parametric approach in science. Okay. Now let's think how we can use parametric approach in statistics. Well, first of all, we usually deal with one variable at a time, right? So we don't have any dependencies in statistics. We have like some random values. So we have some, for example, height or concentration of chloride or anything else. And then we have a lot of different random values somehow distributed. Okay. So we can't feed these values with a known function. But what can we do? We can make a distribution of these values, density distribution, okay? And then try a function, a theoretical distribution that describes the real experimental distribution, okay? So we need to find some theoretical distributions that fits our distribution well, like something like this, okay? And then the idea is the same. We find the theoretical function that fits our distribution. If this fit is good enough, we find parameters of this function, and then we use these parameters to describe the data, because usually theoretical distribution has very few parameters, from 1 to 3. So very, very rarely there are more parameters than 3. So you can use only 3 parameters to describe the whole behavior of your data. You can compare different data sets using these parameters and so on. So that's what we call parametric approach, parametric approach in statistics. Parametric because we describe data using like several parameters, the theoretical distributions. This parametric approach is very efficient, but it will work only if indeed your data follow some theoretical distribution. If it doesn't, then we need to use some non-parametric methods, which we are going to discuss at the end of this course. So now we can conclude this small part about the parametric approach in science and theory. So why we need to learn theoretical distributions if we can always use experimental statistics like quantiles, quartiles, percentiles? Well, it's easy because many different events, measurements, errors, different statistics follow various theoretical distributions. They can be described by some theoretical laws, theoretical distributions. And then we can calculate, we can estimate parameters of these distributions from the experimental data we have, and then we can use this to interpolate and extrapolate to describe what's going on, to find different intervals and compare the different data sets. This approach is called parametric statistics, and most of this course will be devoted to the parametric methods.